speaker is introduced, let me add a few more words. Dr. Suvankar Chakraverty is a scientist. He current to the associate professors and presently the head of the quantum material and device unit of the Institute of Nanoscience and Technology under the Ministry of Science and Technology, Government of India. This is the first and only one Government of India research center dedicated to the nanoscience and technology. Dr. Suvankar he studied at Presidency College, Kolkata. He did his PhD from SN Bose Centers in India, which is most prestigious center for research. And he worked uh, at the Institute of Material Science, Tokyo University, as a GSPS fellow. In addition, he worked at Berlin University, Israel, Basla University, Sweden's. Later on, he also worked at Lincoln University, Japan. His area of interest is the realization of new material with emergent physical properties in the form of thin film, superlattice interface, material with strong spin orbit coupling, magnetic proximity effect, various phases, Rashba effect, unusual electron transport, and topological specs of matters. He has published more than 60 research papers in highly reputed journals that include the Nature Communications. As you know, this is the highest rated journals, Advanced Materials, Physical Reviews, B, etc. And Suvankar, Dr. Suvankar Chakravarty had also received a grant of 8 crore from the Nano mission of Government of India under Department of Science and Technology. On the behalf of the Physics Department, I welcome you, sir, and I request you kindly deliver your talk. Thank you, sir.
Thank you, all of you, especially Jagjivanji, for giving me the opportunity to discuss about what are we doing. And initially, you said that please try to motivate our students, but that is actually a very difficult task to motivate anybody for doing science. It has to be self-motivated. I don't know why I can't. Hello.
Yes, sir, you're audible, sir.
Audible, but I can't present. Okay,
Okay,
yeah,
okay.
yeah, no, it's okay, it's fine, it's fine. It's very difficult to motivate anybody to do
Sir,
science.
excuse me, sir. Actually, still your slide is not okay. Now
Yeah,
it
yeah,
is
yeah,
right.
yeah. I am now presenting.
Okay, okay, sir. Thank you, sir.
It started presentation. Is it started?
Yes, sir. You continue now.
Can you see my slides?
Yes, sir.
Okay. So rather than just give me a second. Yeah. So rather than trying to motivate anybody to do science, what I would like to do is that I will show you what are we doing, and I'm sure you will find that it is not that difficult what we are doing, and you will get motivated through that only. So I'm working at, as you all already said, that I'm working at Institute of Nanoscience and Technology. It is located at Mohali, and we are working, we have different units in this institution. One is based on quantum materials and device. As you know, this is more towards physics, but nowadays science, it is very difficult to disentangle physics, chemistry, and biology, or are entangled with each other, because when you talk about quantum material, then you have to prepare the material, for which you need the knowledge of chemistry as well. And when we say quantum material, what we exactly mean by that? Say, for example, one of the very well-known problem in quantum mechanics. So do you have quantum mechanics already started, right, in bachelor courses, Jagjivanji?
Yes, sir. Yes, it is in second
Okay.
year.
Okay. So one
But we
of
have
the
also, but we
yeah.
have also first year student here.
Okay, so we are not going into the detail of quantum mechanics, just as a motivation. In quantum mechanics, one of the very well defined problem is the quantum well problem, right? So if I say quantum well, then you have a confined potential, and your electrons or the quantum mechanical particles are moving inside this potential well. Now the question is, This is mathematically very easy to define. You define your Hamiltonian accordingly. You figure out your energy eigenvalue, eigenstate, and you find out the solution of this particular Hamiltonian. But if I say how to realize this in a physical system, this is the challenge, and this is what we do in our unit. We try to map the quantum mechanical problems into a material so that you can see this fascinating quantum properties and utilize those properties for the device applications. I'm not going to the detail of this today. So as you have already seen that I did my this basic study from Presidency College, then did my a PhD from SN Bose National Center for Basic Sciences. I got the opportunity to work in Indian Association of Cultivation of Science, Indian Institute of Science, Bangalore, and so on. Finally, I was working in Rike in Japan and University of Tokyo as assistant professor and a research scientist before coming and joining to INST Mohali. So this is our campus at Mohali. I kind of invite all of you, if you get time and if you're interested, please come and visit us. And this is my laboratory, which is known as thin film facility at INST Mohali. It has what is called a pulse laser deposition system, where you can deposit thin film and superstructure. And also you have a physical property measurement system. What is that? You can measure the transport property, that is the electrical property and magnetic property. And you can go to very low temperature. You can go to even down to 2 Kelvin, that is around minus 275 degrees centigrade. And you can apply huge magnetic field up to 12 Tesla. So since many of you might be interested to know what we are doing as a unit or as a scientist, you can go to this website inst.ac.in and then go to Quantum Material and Device Unit. Then you can find out the faculty members' name, job opportunity, and research highlight, and you can figure out which faculty you are interested in. So this is my research group. These are the 3 PhD students who have already finished their PhD. Neha Wadera, she has joined Cornell University as a postdoc. Ruchi Tomar, she is going to join CNRS France. And Nand Kumar is presently working at IIT Delhi. They have finished their PhD very recently. Now, since we have a lot of student friends here, just to give you an idea, if you are interested, then how you may join INST. So after doing MSc in biology, chemistry of physics and material science, with a good score in GATE and NET, you may apply twice in a year. One, the advertisement come around September-October time scale, for which the session start at January, and another comes at May-June time scale, where the session start at August-September. So please go to this website and you have to fill up the form. Based on the application we receive, we shortlist these applications, and the shortlisted candidates are interviewed. Typically, out of 200 applications, 10 are selected per semester for Quantum Material and Device Unit. This is the abbreviation of Quantum Material and Device Unit. We call it QMAD. So today I'm going to talk about, I'm going to give you an idea about what is nano, why nano, how to make nano, and how to see nano. So let me tell you, it is very difficult nowadays to think about your life without science. Why it is so? You start from anything, starting from curing disease, antibiotic, medicine, surgery, then your everyday life, for example, electricity, transport, train, aircraft, anything and everything you cannot imagine without science. So science is kind of integrated part of our life, even if we don't realize. So what do we do as a scientist in INST Mohali? So this is a very problem with scientists. When you ask any scientist what you do, they will say you something by which you will understand that they are doing something great, but you will be failed to understand exactly what they are doing. So if I tell you that I am doing I am working on two-dimensional electron gas with spin orbit with strong Rashba spin orbit coupling based on low-dimensional Datta transistor for spintronic application. It doesn't make any sense to any of you, right? So this is the problem. But today the idea is so you will feel that what is that? But today the idea is completely different. Today we'll try to understand things based on your very basic knowledge and very simplified manner, so that you get a feeling what we are doing and which direction we are trying to go to. Okay. So to understand today's discussion, you need to know only few things. Number one, very simple thing, law of reflection. Then magnetic field produced by a current carrying wire, which is kind of low range law, and the law of conservation of energy. If you understand these three things, which you have learned in your class 8 or class 10 standard, then it will be kind of very easy to understand what we are doing in a very simplified manner. So what is nano, or what is nanoscience and technology? When you talk about nanoscience and technology, the first thing strike into your mind, what is nano? Nano is nothing but 10 to the power minus 9. So if you say 10 to the power minus 9 meter, then it is nanometer. If you say 10 to the power minus 9 second, then it is nanosecond, so on and so forth. So this is the, in this kind of size range, the size of the material really matters. And I'll tell you in the subsequent slides then why it is so that the size really matters. Because if you think of a size of your mobile, the size of mobile, if it is 6 inch or it's 7 inch, it hardly matters. But in nano, 6 nanometer and 7 nanometer are really different, and they shows really different physical property. So when you make the size smaller and smaller, then size effect become very important. To give you an idea what is the size or how small this size of nanometer is. So if you think of a width of a human hair, then it is almost 100,000 times of a nanometer. So you can understand, if you take your hair and you can make it 100,000, break it in 100,000 in width, the size you get is the 1 nanometer. So this is a very important number. Can anyone from the audience tell me what this number is? Okay. If so, this is the problem of this online meeting. I don't know how many of you are present or not. So this is a very important number. This is the size of the, or the radius of this earth. Okay. Now you think 1 million times smaller than the radius of earth. What will be? It will be the size of an apple. So this is, if you take earth and 1 millionth of the smaller of the earth is kind of apple. Now if you make it 100,000 times or 1 million times smaller than an apple, then what you get is a nano size. So you understand, with compared to earth how small an apple is. Now you understand, you consider apple as earth, then the size of a nanometer size particle is like an apple. So you understand how small a nanometer size object is. So now let me tell you why nano are so different in compared to bulk. Let us think that you take a cube with side A. So what will be the surface area of this cube? The surface area of this cube is nothing but 6a square. And the volume of this cube is nothing but a cube. Now imagine that you break this cube into two parts. So you have now sides A by 2, and you have two cubes. So what will be the volume of these two cubes? The volume will remain constant, which is a cube. But now the surface area has been increased from 6a square to 8a square. I will suggest my student friend to try it by yourself. Then you'll get a very nice feeling. Now think that instead of making it, cut it in two parts, you cut it in four parts, 1, 2, 3, 4 in this direction and 4 in this direction. Okay. Now the volume remains same, but your surface area is now increased to 24 a square. And if you cut it into 1 over 8th time, then it becomes 48 a square, the total surface area. So you see that starting from a big size, when you make smaller and smaller, your surface area becomes larger and larger. So you can easily think what will be the implication of that. Say, for example, if you take a catalyst and if you have only one area, then the catalytic activity will be much less than you have many catalysts with many areas. So this surface will give rise to many significant properties, which is very different from the bulk. This is one of the important key feature of nanoscience. Now let's start from very old high school idea. You send the current through a resistance, then a voltage develop because you have resistance. What is the basic what is the basis of this resistance? If you think that you have a very perfectly crystalline material and you are sending electron through this, then the electron can pass through this wire without suffering any collision. This gives rise to what is called low resistive material. It's not this is what is the conductor, but although this is not scattering, it should not be confused with superconductor. This is really good conductor, but not a superconductor. Now, if you take any realistic material, then instead of having this kind of array of perfectly crystalline atoms, you always have some deformation, right? And because of this deformation of this lattice, when you send the electron through this, they scatters. And this scattering, what gives rise to resistance. Now let us think that we have these four wires. Now the question is which wire has a smallest resistance and which wire has a largest resistance. So this L1 has a lowest resistance and L4 has a highest resistance. Why it is so? So resistance is basically proportional to the length of the wire, because if you have a longer length, it scatters more. The scattering, you may have a lot of scattering points and it scatters more. And if the resistance is inversely proportional to the area, cross-sectional area of the wire, if the length remains constant. And if both varies, then the resistance is proportional to length and inversely proportional to the area. And since it is the proportional, then the proportionality constant is what is known as the resistivity of the material. So it is the resistance of the material per unit length per unit area. Now let us think that you take a wire of 1 meter long, of copper wire, 1 meter long, and you are now changing the radius of that copper wire. So please just concentrate on this left hand side view graph. And please note that this x-axis is in a logarithmic scale. Okay, so this is 10 to the power 0, 10 to the power minus 1 in meters. So now what I'm saying that you take an wire, first 10 to the power 0, that is 1 meter radius, and you keep the length constant. Then you change it to 10 to the power minus 2 meter, minus 3 meter, and so on. And you can basically calculate the resistance of this copper wire knowing the resistivity of copper. You can see if you change the this copper wire diameter from 0 means 1 meter to even 10 to the power minus 8 meter, that is around 100 nanometer, sorry, 10 nanometer, then the resistance change is around 800 ohm only. Okay. But if you change it from 10 nanometer and go to 1 nanometer, the resistance change from 800 nanometer to 800 ohms to 80,000 ohm. So by changing 1 order of magnitude of this wire, when you are in nanoscale, you change the resistance by almost 3 order of magnitude. So now one can basically calculate, if you know, if you use this I square RT, then you can basically calculate the energy generated because of sending the current, and that will be converted into heat, right? So this heat will, what will happen? This will increase the temperature of the wire. So if you send the current through a wire, because of the Joule heating, the temperature of the wire will increase. Now you see, this is very interesting. So here I have plotted the temperature change when you send 1 ampere of current through different resistors. You see, when the resistance change up to 10 to the power minus 7 order, that is, you start from a meter, you go to 100 nanometer, your temperature change because of sending current is just 7 degrees centigrade. But starting from 10 nanometer, if you go to 1 nanometer, the change in temperature is 78,000 degrees centigrade. And the melting point of copper wire is just 1000 degrees centigrade, around 1000 degrees centigrade. So what happens? What is the implication? This has a very big implication. Is that if you want to create the electronic circuits in your computer, in your mobile, and so on. So see, when you talk about mobile or your computer, you always talk about what is the storage medium of the system. So if you want to store more data, it means, because you don't want to make your mobile bigger, right? You want to keep your mobile small and you want to store a lot of data there. So keeping the size, total size same, if you want to put lot of data there, then your circuit size has to be very small. But if you want to make your circuit very small, you have to have connector with very thin connectors. But now you see, if you make the connector very thin, then the temperature rise in the connector becomes very high. If you have so much of temperature change, then what will happen? Your system will immediately, it will be melt down and your system will be unstable. So this is one of the limitation of nanoscience. So how to make nanocrystal? So there are two ways. I am first talking with the first way. You take one solid, you can break it. You start continue breaking it, or you can cut it, or you can chip it. You continue doing it until and unless it becomes nano size. So you start from a big one, you grind, cut whatever way you want, and you go to a smaller and smaller and smaller size and get the nano size crystal. So this technique is known as top-down approach. That is, starting from bigger, you are going to a smaller size. Now, there is another approach. What is that? You start from a molecule. The size of a typical atom or molecule is of the order of angstrom. So, angstrom is 1/10 of a nanometer. So, you now start joining this different molecule on the top of each other, and then you finally reach to a nanometer size, at nanometer size substance, the size you want to achieve. This technique is known as bottom-up approach. That is, you are starting from a smaller size from the bottom, you are growing it and growing to a larger size. So it's known as a bottom-up approach. So these are the two usually widely accepted approach in nanoscience. So these are the methods you use to artificially create your nanomaterials. But nano is already existing in nature. So if you think of a spider, spider has a leg which has very tiny, small hair-like structure, and the size of the tip of this each hair is around 10 nanometer. Okay. You start from a beetle and goes to a lizard. So you see this is their legs. It is around 2 micron in size for a beetle, and if you go to a lizard, it has size of the order of nanometer, which helps them to stick on the wall. So these are the naturally occurring nano in the in world, but in laboratory, scientists has tried to prepare mimic this kind of structure. Usually the scientists, what they do, all the research are mainly motivated by the nature, and they have tried to prepare this kind of structure which is known as gecko tape structure. This made out of carbon nanotubes at University of Argonne, and this has a 4 times much more stickier than normally available this lizard feed gecko tape. So you know that in lotus, when you put a water, what happens? The water cannot stay there. It forms a kind of circular structure and it flows away. This happens because of the surface tension. This because of the surface tension, they create a kind of bubble of water, and when they move on the top of this lotus leaf, they also collect the dust particle and so on, and they move. So this phenomenon is known as super hydrophobicity, and because of this, the leaf of the lotus remains clean always. This technique is known as the self-cleaning technique, and this happens because on the top of this lotus you have this kind of nano structure which helps this water to form this kind of spherical shape. So scientists are using this technology to create self-cleaning short and your wearable things, and this is used in the textile industry. So they're using this kind of nano structure on the top of your shirt so that the water cannot stick on your shirt, and when they move on the top of your shirt, they will self-clean your shirt or the wearables. So this is the similar technique naturally used in the body of the shark. They have this kind of structure on their body so that their body remains self-clean. And now people are using this kind of structure on the sheep so that even if the sheep is inside the water for a long time, it remains rust-free. Okay, so one of the fascinating example of this nanotechnology is in your computer, and especially in your hard disk. So what happens in your hard disk? You have magnetic material, and when you magnetize this material in up direction, you define it as bit 1. So basically computer works in a binary state, 1 and 0. So when you magnetize this in an up direction, so you say that you have written 1 in the system. When you magnetize this in a downwards direction, you say that, okay, I have written 0 in the system. So you can write down 1 0 0 1, so on and so forth, by changing the direction of the magnet in your system. So if you take a magnetic material and you apply a magnetic field, then they orient in one direction, and without magnetic field, they are oriented in different direction because of either because they are paramagnetic, or if they are ferromagnetic, then because of the domain structure in the magnet, they have zero magnetization in absence of any magnetic field. When you apply a magnetic field, all the spins are now aligned in one direction, giving rise to a magnetic state of the system. So how to generate a magnetic field? The simple idea is you send a current, and through a wire, then magnetic field is generated. To opposite the direction of the magnetic field, you just start rotating the current in opposite direction, and your magnetic field direction is now changed. So, okay. Why it is not working? Okay.
We visualized as a minuscule block that can be magnetized.
So this is video graphic representation of how this magnetic state in your computer is created. So this is the current is going through this, and magnetic field is produced, and the up down magnetic state in the systems are created. So where is nano here? So think of that you have a terabyte system. It means you have 10 to the power 12 byte per square inch. So what is the size of each byte? The size of each byte is around 40 nanometers. Okay, so this is a real picture of hard disk, and this is rotating, and this is your read and write devices. Okay, so now the question is, nano is so small, so how to see nano? Let us think that you have an elephant and there are blind people around. So how will they feel? How will they see elephant? So this is impossible for them to see elephant, but they can, by touching the different part, they can feel the elephant. For example, somebody touching the ear of the elephant will think that, okay, it looks something like a Japanese fan. Somebody touching this part of belly of the elephant might feel that it looks like something like a wall. Somebody touching the feet might feel that it's like a pillar. So, but if you think, this is terrible, right? Somebody is thinking it is a wall, somebody is thinking it's a Japanese fan, somebody might think it's a rope, somebody is thinking it's a pillar and it's a wall, so on. But if you can cleverly arrange them in a coherent manner, then it may not look very bad. It might look something like this, which is not really a elephant, but it is something which resembles an elephant. So this is precisely the idea people use to look into the nano system. Since you can't see the nano system, you use some technique by which you can make a mapping of the system and say, okay, the system actually look like this. So to understand, one of the technique which we use to understand the see the nano system is based on a technique which is very the basic technique or basic idea is very elementary. It depends on the law of reflection, where the angle of reflection is just equal to the angle of incident. So what happens is the following: you take a system and you have nanostructure, so you can't see them, right? Now you take a cantilever and you shine a laser on the top of this, and you have a very sharp cantilever and a tip. Now what will you do? You move this cantilever from left to right. What will happen? When you are here, then your angle of incident is something, but when you are down here, then your angle of incident will change. And accordingly, your angle of reflection will change. Now keep a photo detector here. What is a photo detector? Photo detector is a detector on which if a light is shining, it creates an electricity. So this photo detector can also detect where the light is shining. So now if you move this cantilever from here to here, your angle of reflection and angle of incident both are changed, and this light was initially here, now it has moved from here to here. So by looking into the motion of this light which is on the photo detector, you can map out how this surface looks like, as the people has done that for the elephant I have discussed previously. Okay, so this is the scenario in when this tip is here and when the tip is here, your light is here and here. Okay, so now I show you some real, so this technique is known as atomic force microscopy technique. So I show you one real image of that, how it works. Okay, so this is the tip I was talking about, and it will try to look into, so it is now going down, and so this is the tip, and it will try to detect some very small feature on the surface of a material. So this goes down and this will move on the top of the surface, and this wants to map out this small object on the top of a surface. Okay, and this is one of the so you can see that this is 4.4 nanometer in height. It looks like a steps and terrace. This is made in INST Mohali by us. So this is a real structure of nanostructure, and this is actually an image seen by atomic force microscopy. But there is you have to be very careful. There is a chetavni that if you are not careful enough, and if you can't put your knowledge coherently to figure out what you have seen, then instead of looking into an elephant, it might look something which is very terrible, and you might end up with something which looks like this. So thank you, all of you. And if you have any question or anything, you may please feel free to ask me. Yes.
Sir,
Hello.
can you hear me? Is my voice
Can't
audible?
hear you. Oh, I'm sorry. I might, this is turned off. I'm sorry. Yeah, please tell me. Yeah.
Sir, now is my voice audible?
Yeah, it's audible very much.
Sir, why do we use atomic force microscopy and not field emission microscope? Because it has a larger
No, 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 no. Yeah, yeah,
visualization.
yeah, definitely, definitely. There are many ways to look into different things. So it depends on what you want to see. So this is field emission type things and mostly for transmission mode, right? And this atomic force microscopy are mostly for looking into the surface morphology. So what you want to see and how you want to see depends on that which instrument you want to use. Okay, so definitely that you can also use. I'm not saying that atomic force microscopy is the only one, but this is one of the possible instrument which can be used to see the nanostructures. Yeah. Does this make any sense, or you have any other question?
Yes, sir. One more question I need to ask.
Please, please.
Sir, when you told us about how to synthesize the various nanoparticles,
Yeah,
so can we use a way in which we vaporize the material and then we deposit
yeah,
on a surface so
yeah,
that it
yeah, yeah.
acquires a nanostructure?
Definitely, definitely. So there are many methods for what you are saying, that is basically used for preparing the thin films or the superlattices or superstructure. For example, you can use either chemical vapor deposition type system or physical vapor deposition type system. We especially in our institute we use physical vapor deposition type system, where you use pulse laser deposition, molecular beam epitaxy, and so on, and sputtering system, and so on.
Thank you, sir.
Yeah, please.
So,
Yeah, please.
you gave an example of how we can make an elephant out of various things that we touch. We can
Right,
create a model.
right,
And similarly, we do not see actually nanoparticles. We can
right.
only create models. But how can we tell whether the model that we created was correct or not? We are able to see which
Yeah,
model
that's
of
it.
elephant you
Yeah,
shown us was correct, but which model of
yeah,
nanoparticles is correct? We won't know that because we don't actually see them.
yeah, exactly. So this is a very good question. So the point is that is why it is the characterization techniques are so important. So that is why when you try to publish a paper or you try to understand the physics or something, one method doesn't is not sufficient enough. You use different method and try to see if they are coherent with each other or not. For example, you prepare some nanoparticle. Okay, then you perform what is known as X-ray diffraction. From X-ray diffraction also people can talk about the size of the nanoparticle. You use that technique, number one. Then you use this AFM, atomic force microscopy. From there you try to see how these particles look like. If these two kind of match very well with each other, then you can be confident enough to say, okay, see, this is the size of the nanoparticle in my system. Okay.
Yes, sir.
Yeah. If you have any more question, I'll be happy to answer, or you feel free to email me in my email ID. I think Jagjivanji already he has, so you can take it from him as well.
Yeah, I invite questions from the teacher sides.
Yeah,
Hello.
yeah, please. Hello.
Yeah, hello, sir. Are these facilities like this film preparations or calculations, they are free or they are chargeable at institutes?
Uh, this is a very tricky and difficult question. It depends on many factors. So if you start working in a collaborative mode, then you can always access them in free. But sometimes you think that, okay, it's fine that you want to measure some small things and you don't want to really have a collaboration, then you can do it on a payment basis as well. So it has both the mode possible.
So can we submit a proposals or some project type, like something like this, that
Yeah,
so that we
definitely,
have.
definitely. Or if you want to have some small measurement to be done, you can send it. I will try to measure it for you. So it's not a big deal. And anytime any of your student or colleague wants to contact, they can send me an email. And we have many kind of also internship program for the students, and they can come and stay here for 3 months.
Uh,
Okay,
Dr.
thank you, sir.
Jagjeevan, I am allowed. Dr.
Yeah,
Jagjeevan,
Yes, sir. Yes, sir. Yeah,
that
Abhinav,
is,
Manya,
yeah, I am
hello.
Ashok. Hello.
yeah, you
Yeah,
are audible.
yes,
You
sir.
are
You are
audible.
audible. Yes, sir. Yes, sir.
That is what I wanted to ask from Professor Suvankar.
Yeah,
That is there any provision that our student can visit your
yeah,
institution,
definitely,
see
definitely.
the first-hand information they could have, they can see, because it is our experience that whenever a student visit any place, they get very fascinated and attracted, and many of them further pursue higher studies or research as career. So
Yeah.
is there provisions such?
Yes. There are
Not
many
right
provisions.
now, but in future, because when we expect that the COVID situation will improve and so on.
Yeah, definitely. As I said, in case if anybody is interested, tell them to write it to me. I can forward it to the concerned person, or tell your student to go to inst.ac.in, and there they might find the people who are dealing with this internship program, and they must write to them.
Okay,
And we also organize many online seminars and this popular science lecture. From now onwards, if you are interested, I will send you the link, and those who are interested may join also.
please, thank you.
Yeah.
Thank you, sir. Now I invite Professor Ashok Kumar, the head of the Department of Physics, to give a vote of thanks to the speaker and to the audience.
Uh, Thank you, Dr. Jagjeevan. It is really a great privilege for Physics Department of Ramjas College. It's all faculty members and students that we have today. Uh, Such speaker, extraordinary speaker, I would say, and I must congratulate and thank Dr. Suvankar in the sense that I heard the lecture, listened the lecture from beginning to end, and found that I think you have done tremendous work on it, especially making it for our undergraduate students. It was so simple, so elaborative, and so clear. So thank you very much. And on behalf of the Department of Physics, Ramjas College, I thank you. Uh, Thanks a lot for this wonderful lecture. And I think that students would get fascinated and attracted in pursuing their research and opting this as a career. And I would also request you to be available whenever we request you for another kind of, or rather for advanced kind of lecture in future. Okay. Thank you very
Sure,
much,
sure,
Dr.
sure.
Subankar. Thank you
Thank you.
thanks to Dr. Jagjeevan and the faculty members who
I would
the
like to ask
students,
something.
all the students who attended this uh, uh, conference. I'm sorry, this seminar. Okay. Thanks again to each and every one. Thank you very much. Dr. Jagjeevan, please.
Thank you.
Yeah, thank you, Ashok, sir.
Yeah, I would like to ask something.
There's some question, I think.
Yes,
Yeah,
yes.
please.
First
Ashok,
of
sir,
all,
please
sir,
kindly mute.
this was a very amazing session and very informative too. And like you talked about internship, so I wanted to ask how to join the internship actually. What are the steps to be followed?
So I am not very much aware of this process, but you may send whoever wants to join. They can say later. They can send me the CV or something to me. I may forward this to the concerned department, or you may go to our website, as I said, in inst.ac.in, and directly write to the concerned person. Or if somebody wants to work with me for some time, they can directly write it to me. But for the time being, I'm sorry that I don't know the exact detail how to do this.
Okay, sir. You can share your email, right? If you could just share your email
Yes, Riya, we
again.
have. No, we will.
Yeah,
Yeah,
okay,
We,
okay.
we have that in
yeah.
the poster. We have already shared.
Poster, and also if you go to inst.ac.in, then in the quantum material and device unit, not only me, you can find many faculty members. They're all doing great job. So it's not that you have to join me, you can join anybody of your interest. So don't restrict yourself. That will be my suggestion to anybody.
Okay.
It's
Thank
a
you so
free
much
world.
once again,
Yeah,
sir.
yeah, yeah.
This was
Please.
an amazing session.
So are you from physics background, or which background are you
Yes, sir.
from?
Physics background, final year.
Final year. So I will also suggest you to look into chemistry, biology, because this interface is now more important. So
Yeah,
if you
right.
do physics, it doesn't mean you have to work on physics only. We have people working here on hyperthermia. It's a cancer based, but the basis is physics. It's a nanomagnetic material and their relaxation dynamic. So you go to our website, look into the site and the profile of different faculty members. Then you write to me directly. Okay.
So, sir, is the research only limited to the nanotechnology or anything that
Yes.
we want?
Yes.
Okay.
Fortunately or unfortunately, yes. This is limited to
Well,
nanotechnology only.
okay. Thank you so much
Yeah.
once again, sir.
Yeah.
Yeah. Any more queries from the student sides? Okay, thank you. Let us once again thanks to Dr. Suvankar Chakraverty. Yes, thus, sir, you have presented a very simple, interesting way, and it was really stimulating to all of us. Uh, I hope most of us might have interesting to know more and more about this, because these are
Please.
the young minds, and they have to think about this. So
Okay, by
definitely,
just 1 second. We have one of our review article which is just published in Advanced Material. You might know Advanced Material is one of the
best,
highest.
yeah, general,
Yeah.
highest
So
rated.
yeah, I am sending the link in this text message so that anybody can have a look. It's is it there?
Yes, sir. Copy got it
Yeah,
here, sir.
yeah. So anybody want can just click on this and have a look at that.
Thank you very much, sir. So nice of you, sir. Thank you, sir. Thank you very much,
Thank
sir.
you. Thank you.
Thank you to all. Thank
Yeah.
you.
Bye.
Now, it is
Abhinav,
completely
yes. Go ahead.
yes. I was just concluding it. Thank you. It is completely apparent when I say that we are really looking forward to another lecture by Dr. Suvankar Chakraverty, and we hope that we find such an opportunity very soon.